In this part of chemistry, we are going to talk about equilibrium and reactions. Okay, if we have a reaction that A plus B gives me C and D. As we know, we call this part reactants, and we call these ones what? Products, because we read them from left to right. This is a reaction. Okay, so reactants on the left and products on the right. And this reaction now, if it goes only from left to right, that means it goes only one way. We call it forward reaction. Okay, what about if this reaction also goes back in reverse? That means these products, they can also produce, they can go in reverse as a reaction, and they can produce what? The reactants themselves. In this case, we call this reaction what? Reverse reaction, and we give it this arrows. So that means you have one arrow to the right and one to the left. So that means in this case, this reaction is called reverse reaction, and it goes forward and it goes what? Backwards. But we still call these ones reactants and these ones what? Products. We still read the reaction from left to right, reactants and products, even if it is reversible and it goes in both ways. Good. If this reaction now, we have reactants A and B, and we have products C and D. And this reaction, as we said, it goes forward to produce C and D, then it goes in reverse to produce A and B. Okay, if this reaction now is in a closed system, so it takes place in a closed system, and heat is constant, what would happen for this equilibrium, or what would happen for this reaction? It would reach a point or a state that is called equilibrium. Okay, what is equilibrium? Equilibrium states where the rate of this reaction while it goes to the right, it equals the rate of reaction while it goes to the left. In this case, it's the rate. That means the amount of a change of reactants to go to the right is the same to the left. So in this case, as a rate in concentration, in this case, we call it what? Equilibrium state. Equilibrium state, and the concentration is constant here. Okay, now we understand when do we call a reaction that is as a reversible reaction, and understand when it reaches a point or a state that it is called what? Equilibrium state. Good. There is something we call it constant of equilibrium. Constant of equilibrium. This constant of equilibrium, it is a ratio. It is a ratio. Okay, what is ratio here? For example, now in this reaction, if this one has a factor here that is A, which is number of moles, and here number of moles B, and here number of moles C, and here number of moles what? D. If we have now this reaction and it is at equilibrium, how do I write its constant of equilibrium? Good. We write it first, we write the products C, and also we write the product what? D. And we put both of them to the power of their number of moles. So here's the power of C, and here's the power of what? D. These ones products. Okay, what about reactants? Same thing. So you write in the denominator now A, concentration of A, and concentration of what? Of B. Then each of them is to the power of its number of moles. So here is A, and here is what? B. So this is how to write the constant of equilibrium, and it is a ratio of concentration, as you see, of products over reactants, and each of it is into the power of its number of moles. Good. We understand now how to write constant of equilibrium, and if we have the concentration now of the reactants and of the products, we can find the value of constant of equilibrium. Okay, if we can take example. If we have this reaction, which is I2 plus H2, reverse reaction, it gives HI. How can we write the equilibrium constant? How can we write it in this case? Okay, to write the constant of equilibrium, you need to focus on products and reactants. This is one point. And another point, you need to make sure that this equation is balanced. Good. And a third point, you need to focus on the states of products and reactants. Here, the state here is gas. Good. And here the state is gas. Okay. And here the state is of gas. And to make it balanced, here is 2 and here is 2, so we write here 2. Now it is balanced and the states are written on it. So now I go to write what? Equilibrium constant. So equilibrium constant, as we said, equals products, which is HI, over what? Over reactants. And here now, I2, and here is what? H2. But now both of make sure now you write the power as the number of moles. What is the number of moles here? 1. So it's not written. What is the number here now? It's 1. So we don't need to write 1 here as power because it is known that it is what? 1. But here now, as you see, have the power 2. So you write here what? 2. This is now how to write the equilibrium constant. And pay attention, equilibrium constant is written for only gases. That means if one of the states of a product or of a reactant is not gas, that means it is solid or liquid. In this case, we didn't write it and we didn't include it in the equilibrium constant. Why? Because solids, here we are talking about concentrations. And concentrations are usually used for gases or aqueous solutions. So solids and liquids, they are pure. What does it mean they are pure? That means if I have like carbon is pure. So that means we didn't use concentration for carbon because its concentration is constant. So that means we didn't include solids and liquids in equilibrium constant because they are pure substances and they have constant concentration. So we didn't mention them, just we write for gases. Okay, for this example now, just if we use it as numbers, if we have a concentration here of hydrogen like 5 molarity, 5 molarity, and the concentration is here 4 molarity. And the concentration of HI, is 10 molarity. And we know what does it mean, molarity. Molarity is the unit for concentration when it is number of how many molecules or how many particles of solute inside the 1 liter of the solution. Okay. So in this case now, if you apply these numbers in this equation, it's going to be now, as you see, HI here is 10 and it's going to be 10 squared over the I here, it's going to be 4 multiplied by what? By 5 here. So that means it's going to be 100 over 20. That equals what? 5. So that means the constant of equilibrium here is 5, as you see, and it is products concentration over reactants concentration. Okay, we take another example now, just another example to see how we write the equilibrium constant. If I have here H2O2, and it gives me here H2O plus O2. Okay, first I have to balance this equation. So that means here we write 2, here we write 2. As you see here, now we have hydrogen left, 4 hydrogen left, and 4 hydrogen right, and we have 4 oxygen left and 4 oxygen right. Okay, second, as we said, we have to check the state. Here is liquid, and here is gas, and here is gas. Okay, good. Now, how can we write the equilibrium constant? As you said, equilibrium constant, it equals the products, which is the concentration of H2O times the concentration of what? Of O2. And over what? The reactants. But what are the reactants here? The reactants are, as you see, H2O2. But what is its state? Its state is liquid. So that means when you write here H2O2 and it is liquid, just eliminate it. And that means no need to use it in the constant of equilibrium as long as it is liquid or solid. We only use gases that are in this question. So that means this one just will be what? The equilibrium constant, but now we still have to write the power. What is the power here? Is 2, so that means we write here 2. What is the power here? Is 1, so we don't need to write here. So that means this one will be the answer for the constant of equilibrium. So what we understand now, what we understand till now is a reaction, it is called reversible if it goes from reactants to products and also from products into reactants. And if the rate of forward and reverse reaction, if the rates are equal, so in this case we call it what? We call this reaction, it is a reaction at equilibrium state. And when it is in an equilibrium state, we have equilibrium constant. An equilibrium constant, it's an indicator for this equilibrium, and it equals the concentrations of products over the concentrations of reactants. Okay, now we're going to talk about another point. If we have a system now that is, or a reaction in a system that is at equilibrium, good. Is there factors, this is the question now, is there factors that affect this equilibrium state or no? So here we have A plus B gives me C plus D. This is now a reverse reaction, and it is at equilibrium. It is at equilibrium. What are the factors now that can affect this state of equilibrium? Okay, we have these factors and we need to memorize them. Factor number 1 is concentration. Factor number 2 is temperature. Factor number 3 is pressure and volume. So these ones now, these 3 factors, by the way, and pressure and volume, we include them like one because they mean the same thing. We're going to explain that. So concentration and temperature, that means if I change the concentration now, if I change the concentration of any product or any reactant, this state of equilibrium will be affected. This state of equilibrium will be affected. But keep in mind, these ones now, they can change the state of equilibrium. That means they shift. This equilibrium will be shifted either to the right or to the left when these ones are changed. So when concentration is changed, this equilibrium will move to the left more or to the right. Temperature also will play the same role, and pressure and volume will play the same role. But look, the constant of equilibrium, because constant of equilibrium, it is a ratio. That means it is denominator and numerator and denominator. So as we know of a ratio, if I have 1 over 2, this is a ratio, 1 over 2. If I change it to be 2 over 4, if I change it to be over 4, I change the numbers 1 to be 2 and 2 to be 4. But is it still the same ratio 1 over 2? Yes. So that means whether you use these two numbers or these two numbers, the ratio is still the same, which is half. So that means when I change concentration, when I change temperature, when I change pressure and volume, okay, these ones now, all of them will change the state of equilibrium, and this one will not change. Okay, when it is changed, constant of equilibrium, I'm gonna write it here as map and keep it in mind. So this one now does not change the constant of equilibrium. This one now does not change the constant of equilibrium. But this one now, this one here, which is the temperature, and we're gonna study it, it changes the constant of what? Of equilibrium. So again now, we have three factors that change equilibrium: concentration, temperature, pressure, and volume. These ones now, they can change the state of equilibrium. Good. But one of them can change both the state of equilibrium and the equilibrium constant, which is only what? Temperature. I hope that is clear. So that means whenever I change the concentration or pressure or volume, constant of equilibrium will not be changed. But if you change temperature, constant of equilibrium will be changed. And I hope that is clear. Okay, how are they going to be changed? Look, we're going to study each case, how it changes what? The state of equilibrium. So if I have here now A plus B gives me C and D. We have here something called Le Chatelet what? Principle. What is Le Chatelet principle? What is Le Chatelet principle? Le Chatelet principle states that if the reaction is at equilibrium, any stress is applied on this equilibrium, the reaction will go to the direction that relieves this stress. What does that mean? So I'm gonna give you one sentence that is very important that summarizes Le Chatelet principle. Just you memorize it and use it. But look here, now we explain it on the first point here. This is concentration we set. Concentration now, this system is at equilibrium. A plus B gives me C and D. Okay, if we increase the concentration of A, if we increase the concentration of what? Of A. Okay, we're going to increase this concentration. That means now we are increasing the concentration of A, which is a reactant. What will happen for the system? That means now we are making stress. Now we are applying stress on the system, on the equilibrium state. What will happen in this case? Based on Le Chatelet principle, it stated that if a stress is applied on this equilibrium, the reaction will shift into the direction that relieves this stress. So when you increase now A, the concentration of A, the reaction now will go forward more to the right or reverse to the left. So look, if you increase A, the reaction will go to the direction that relieves this increase of A. That means it will go to reduce the amount of A. So which direction now will reduce the amount or the concentration of A? Is the direction to go to produce C and D. So that means if A increased, the direction will go where? To the right. Why? To use this A. To use it, that means to relieve this stress that happens to A. It could happen now if we increase D. Instead of A, we increase D. If we increase D. In this case now, the reaction will go in reverse. It will go to the left. it will go to the left. Okay, that means now if we increasing, what about if we decrease? Will be the opposite. If we decrease A now, if we decrease A, system is at equilibrium. If we decrease A, what will happen? The system will go left to substitute A that was decreased. Same thing if we decrease D, the reaction will go to the right to substitute. So I'll give you one sentence now that summarizes this. You can memorize this one. If you memorize these two, you will understand Le Chatelet principle easier. How? If you add, this is the reaction says, the equilibrium, the reaction that is at equilibrium will say these sentences. If you add, I will use it. If you add, I will use it. If you reduce, I will substitute. What does that mean? Look here now, if we apply this one here on this reaction. Look, if you add, I'll use it. If you add, I use it. That means if I add concentration for A, if I add concentration of A, the reaction, what will do? The reaction will use it. Will use it, that means we'll use the A. We'll use the A to what? To produce the other side. That means if you increase the concentration of A, the reaction will go to the right side to use this increase of A. Good. What about if I decrease A? What about if I decrease A? If I decrease A, what will happen in this case? The system says, if you reduce it, I will substitute. So if you reduce A now, the system will go to substitute what you reduced. So that means it will go from right to left in reverse reaction to substitute what has been reduced. So that means we understand now for concentration. That means when I'm talking about A, it's the same for B, it's the same for C, it's the same for D. Same thing. Same thing for all of them in concentration. If you add, I'll use it. If you reduce, I'll substitute. And I hope that is clear. Okay, this is now, it happens, by the way, for both, for concentration and also for temperature. Okay, in temperature now, we have two types of reactions. In temperature, we have what? Two types. We have A plus B plus heat gives me C plus D. And this one here now, this reaction is endothermic reaction. This one is what? Endothermic reaction. Okay, what about exothermic reaction? Exothermic reaction, it is A plus B gives me what? C plus D plus heat. So in exothermic, the heat is a product. In exothermic, the heat is a product. And in endothermic here reaction, the heat is a reactant. So look here now, the same thing you apply this one as Le Chatelet. You apply this one here also for temperature. Okay, if I apply it now, look here now how I apply it for endothermic reaction. This is now endothermic. What will happen if we increase heat in endothermic reaction? Look, if you increase the heat, that means you're increasing the reactant. It is a reactant here, heat is endothermic, because endothermic reaction, it takes heat to produce products. Why exothermic? It produced products and produced heat with them. So if I'm talking now about endothermic, it's not the same when I'm talking about exothermic. So I have to, when I'm talking about temperature, when I'm talking about what temperature? If I'm talking about concentration, in general, it's the same, whether is it endothermic or exothermic, it's the same when I'm talking about the point of concentration. But when I'm talking about the point of temperature, I have to understand whether is it endothermic or exothermic reaction. Okay, endothermic reaction, if you increase the heat, if you increase heat or temperature in endothermic reaction, what will happen? As we said here, if you add, I will use it. So that means since it is now here in the endothermic here, and you increase heat, the reaction will use it. That means it will go what? Forward to produce what? C and D. So if you increase the heat in endothermic reaction, the reaction will go to the right to produce C and D. That means it will go to produce more products. Okay, what about if you decrease heat in endothermic? In endothermic, if you decrease heat, the reaction will go to substitute, as we said. The reaction will go to what? To substitute. So if you reduce the heat or the temperature in the endothermic, the reaction will go to substitute, so it will go in reverse reaction to produce more reactants, such as A and B, and also the heat, because they are reactants. Good. And as you see, for exothermic, it's exactly the opposite. How? Heat now is a product. Heat is a product here. Okay, what will happen now if we increase heat? As we said, if you increase, that means you add. If you add, I'll use it. The reaction will use it. So if you add heat now in the exothermic, the reaction will use it. So that means the reaction will go to the left to produce more reactants. That means it will use this extra heat. Okay, what about if you decrease heat in exothermic reaction? If you decrease heat, as we said here, if you reduce, what will happen? I'll substitute. So that means if you reduce heat now, an exothermic reaction, this reaction will substitute this heat. So that means it will go from left to right to produce more products, and heat is one of these products. I hope now you understand the SATI principle based on concentration and temperature. And as we said, concentration and temperature are factors that affect the equilibrium, state. And eventually then, if you change the temperature and change the concentration, then you stop again, the reaction equilibrium will come back to its state of equilibrium where it has the same ratio, same K equilibrium, which is constant of equilibrium. Okay, now we said the factors that affect the equilibrium state or position are concentration, temperature, pressure, and volume. Okay, we understand now concentration and temperature, how they change the position or the direction of what? Of the equilibrium. Okay, we're going to understand now how pressure and volume it change the equilibrium. So this is now the third point, which is pressure and also what? Volume. I'll take just one example as a reaction, just to understand how these ones they change. If I have carbon monoxide plus hydrogen as the reverse reaction, so we have carbon monoxide plus hydrogen, then it gives us methane and also what? Water. Just to balance this one here, as we know, we have to balance it first, and we write the state of each of them. Here is gas, and here is gas, and here is gas, and here is gas. Good. So all of them now, as you see, are gases. Here, to balance it here, carbon 1, 3 carbon here. Here now we have, as you see, 1 carbon, and here is 1 carbon. Good. And here you have 6 hydrogen, and here you have 4 hydrogen, and here is 2, so that means you have 6 hydrogen. And here you have 1 oxygen, and here we have 1 oxygen, so that means this equation now is balanced, and the states are mentioned, which is gas, 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 gas. Okay, good. The question now, if this equation now, or if this reaction now is at equilibrium state, okay, what will happen now if I increase the pressure or I decrease the pressure, or I increase the volume or I decrease the volume? What will happen for this reaction? What will happen for this reaction if I increase or decrease pressure or volume? Look, this one now, as you see, this reaction is in a closed system. as we said, as we mentioned earlier. That means since it is at equilibrium, that means it is in a closed system. Again, what will happen now if I exert pressure? If I exert pressure here, what will happen? When you exert pressure, that means you are reducing the size. You are reducing what? The size of this container. That means you are, so when you increase pressure, it means directly you are decreasing the volume. So when they tell you increasing the pressure, you have to put in your mind, it's the same time like when they say they decrease the volume. So it is one idea. Increasing pressure, it means, in other words, it means decreasing the volume. Good. What will happen in this case? If I'm increasing the pressure, so that means I have only two cases here. When I'm increasing the pressure or decreasing the pressure. And it means in another way, I'm increasing or decreasing the volume. So if you understand it with pressure, that means you already understand it with volume. Good. So when I increase pressure now, that means I'm decreasing the volume. In this case, the reaction will go to the side of the less number of moles. Why? Because now when the volume decreases, pressure increases, volume decreases, that means the container will be smaller. So in this case, the direction will go to the side where it has less number of moles. Okay, how many moles now on the reactants and how many moles on the products? Here is number of moles. Here is 1 mole and here is 3 moles. And here is 1 mole and here is 1 mole. You see? So on the right side, they have 2 number of moles. Here, 2 moles. And on the left side, they have here 1 and 3, so they have 4 moles. So that means now, if you increase the pressure, that means you are decreasing the volume. In this case, the reaction try to balance, to try to relieve this stress. So it will go to the smaller number to make itself smaller. So it will try to go to the less number of moles. That means it will go to the right. It will go to the right. So this reaction will go to the right when I'm increasing the pressure or decreasing the volume. Or decreasing what? The volume, it will go to the right. Okay, what about if I do the opposite? What about if I do the opposite? What about if I decrease the pressure? If I decrease the pressure, that means I'm increasing the volume. So if I'm decreasing the pressure, that means I'm increasing what? The volume. In this case, the reaction here will go to the left or to the right. So if you are increasing decreasing the pressure, that means you are increasing the volume. That means you are making the size greater. So in this case, this reaction will go to be free, will go to maximize itself, will go to the higher number of moles. Where is higher number of moles? Reactants or products? As you see, here is 4 and here is 2. So it will go to the left where there are 4 number of moles. That means it will go to the side of greater number of moles. And I hope we understand how pressure and volume now change the direction or affect the equilibrium state. So these ones now that we mentioned, concentration, temperature, pressure, and volume, they change the equilibrium state. Okay, what about now just here, the constant of equilibrium? The constant of equilibrium is different from the equilibrium itself, which is the position. So these factors that we mentioned, they change the equilibrium state, the position, the direction. But equilibrium constant will remain the same. Will remain the same even if you change concentration, even if you change pressure, even if you change volume. Constant of equilibrium will remain the same. But what is the factor that also it changes the constant of equilibrium? It's only temperature, and keep that in mind. Only temperature. Okay, here now, how the temperature it changed the constant of equilibrium. As we know, if we are talking about equilibrium and temperature, we are talking about endothermic and also what? Exothermic reaction. Good. And when we are talking about exothermic and endothermic, we are talking about temperature and what? The relationship between temperature and what? Constant of equilibrium. We are talking about temperature and constant of equilibrium. Okay, pay attention to these points. Pay attention to these points. Here now, in endothermic, the relationship here is directly proportional. Keep that in mind. Is directly proportional. And the relationship here is inversely proportional. Here is directly proportional and here is inversely proportional. If you memorize these ones, the questions will be easy. What does that mean here? That means in endothermic reaction, if you increase the temperature, that means you are increasing the constant of equilibrium. Why? Because the constant of equilibrium, if you remember, constant of equilibrium equals products and over what? Over reactants. So when you increase the temperature in endothermic, as we said, this reaction will use it so to go to the right, so to produce more products, more denominator. So that means it will be denominator greater than the denominator. So in this case, the K itself will increase because numerator will increase more than the denominator. Good. So that means what do you need to remember? What do you need to remember? Just remember these ones. Remember these ones. How? In endothermic, the temperature with the constant of equilibrium is directly proportional. So that means if one increases, the other one will increase as well. If one decreases, the other one will decrease as well. In endothermic reaction, I'm talking about temperature and constant of equilibrium. In exothermic, the relationship between temperature and constant of equilibrium is inversely proportional. Just to memorize it. That means if temperature increases, constant of equilibrium will decrease. If that one decreases, that one will increase. So you understand now what are the factors that affect the equilibrium state in general, and what are the factor, which is heat or temperature, that it changes it's the only factor that it changes what? The constant of equilibrium. And the last point now, we're going to understand what is something we called KSP and QSP. These ones are just special cases of constant of equilibrium. This one is a special case of constant of equilibrium, KSP. It is called solubility product constant. Solubility product constant. And this one is called ion product. It's called what? Ion product. Good. These ones just special cases of what? Of constant of equilibrium. So if we are talking about salts that are slightly soluble, we will use KSP instead of constant of equilibrium. But it's the same idea. And here, if the state is not at equilibrium, just instantly we want to take it at a specific time, we use QSP. No need to go into its calculations. It's not required to go into its area, but you need to understand what is this one called and what is this one called now. And you need to remember that you have three states. What are these ones? You have when KSP is greater than QSP. And you have one state when KSP equals QSP. And you have third state when KSP is less than QSP. Okay, in this case, what will happen? Just you need to remember, when K is greater, that means this solution is unsaturated. Unsaturated, that means it can add more ions. It can. So that means now this is unsaturated, while in the other one here, it is saturated. And here it is saturated. So you have two states where they are saturated, and you have one case that they are unsaturated, and also related to precipitation. So we need to understand the relationship between KSP and QSP and which one is greater, and when they are, one of them is greater or equal or less, and whether it is saturated or unsaturated for the solution. Or the next one, we need to understand, will there be precipitation or not? Whether there is precipitation or not. So in the first case here, there'll be no precipitation when the KSP is greater than the QSP. Okay, what about if we are talking about the second one? There is no also what? No change. And on the third one, there will be precipitation. There will be what? Precipitation in this case. I hope we understand this lesson perfectly related to constant of equilibrium and equilibrium in general and what the factors that affect. Thank you so much. See you in other videos.